Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will start talking about properties of least squares estimators in the multiple linear regression setting. Okay? Our main goal in this video will be showing that beta hat is an unbiased estimator of beta. Let's begin. So let me give you an idea of what we're going to be doing next. First, we are going to talk about a proposition, a result, if you will. That result has to do with the expected value of linear combinations of random vectors, of a random vector. Okay? Once we have that proposition, we are going to use it to show that the least squares estimator beta hat is an unbiased estimator of beta in the multiple linear regression model. Okay? Okay. Here we go. Proposition. So we have a matrix A, which is a matrix of constants. Okay, it's fixed with dimensions, say R by N, and then we are going to have a vector C be a fixed also vector, right? So a vector of constants, nothing random there. And finally, we have a random vector y, dimensions m by 1. And then we use these guys, that matrix A, that vector of constants C, and that random vector, we combine them in the following way to form a new random vector. Okay. So what this proposition says is that the expected value of A times Y plus C, where A is a matrix, now Y is a random vector. It is not a random variable, meaning it's a random vector, remember, is a vector such that its elements are random variables, right? Okay. So, we have this, and this is something similar to what you have dealt with when dealing with random variables, right? That if you have the expected value of a sum is the sum of expected values, the expected value of a constant is the constant itself, but in this case it's not just a constant, it's a vector of constants, and that if you have the expected value of a constant times a random variable, you get to factor out that constant, and then expected value of A times Y is just A times expected value of Y, but Y was before just a random variable, meaning a, just a one, it had dimensions 1 by 1, right? But this guy is a random vector, and again, a random vector is such that each of its elements is a random variable. And now this guy here is a matrix, no longer a constant. Okay? Okay, so let me give you an example And after we discuss that, we're going to see that what we did for that example holds, in general. So say that instead of an m by 1, let's talk about a 2 by 1 random vector. Okay, so I don't have to write that much. We have oops, that random vector is formed by 2 random variables like that. Okay, makes sense? So each of these guys is a random variable, so that's a random vector. Okay, no problem. Now, the expected value of a random vector is the expected value. It's a vector that contains the expected values of its elements. So the expected value of y, in this case, it's going to be a 2 by 1 vector that looks like this. Let's just compute the expected value of y1, the first element, compute the expected value of the second element, and then just paste them, create a vector, and that's it. That's the expected value of an that's the expected value of a random vector. Okay. Now, say that we have a 2 by 2 matrix. Okay. Let me write that down like this, with first element a11, then we have a12, a21, a22. Okay, no problem, right? Just a generic 2 by 2 matrix. And now let me write down a generic 2 by 1 vector C. And we know that those guys, the elements of C, are going to be just constants. Okay, so we have C1, C2. Great. Okay, so now we have a particular case of our proposition, right? Okay. Now let me compute that expression, a times y plus c. So a y, which is 2 by 1 by the way, plus c. So clearly, right, we can do that multiplication. It's going to be 2 by 1, the result of multiplying a and y, and plus a 2 by 1 vector. We get to add them up, so the result is going to be 2 by 1, right? Okay. So now let's find this. We could rewrite, if you do the algebra, it's going to be that matrix A11, A12, A21, A22 times Y1, Y2. That's Y, right? So actually let me copy paste this guy, it's going to be useful, and I'll be able to save some time here. So when you do that product, it's this guy times the vector y, so it's going to be y1 plus, it's going to be the other one, A12 times y2, right? And something similar happens with this guy here, plus, and then I have y2 here. But now can you see that when we do that product, this is a 2 by 1, right? Okay, let me write that down there. 2 by 1 plus this guy, C1, C2. Which is also 2 by 1. Well, it's here. Let me copy paste this. There we are. Okay. So let's continue. But this, right, is just going to be this guy plus this guy. I just want this one. Plus C1. Then I have something similar here. That would be the second element. This should be Y1. There. This one should be Y1 as well. Let me fix it. There. Okay, so much better. This plus C2, right? So that's our 2 by 1 vector. This is the first element, this is the second element. No problem, right? Okay, but now what I want you to see is that when you want to find the expected value, and this is just, let me write it down here, a y plus c. We already have here the dimensions, so I'm going to leave it like that there. It's already clear that these two guys are 2 by 1. Okay, so anyway, when you want to find the expected value of that 2 by 1 vector, what we mean is just, find the expected value of the elements that form that vector. So that's what we mean. Right? Now, we can do a little bit of algebra inside each of these elements, right? these guys, y1 and y2, are random variables. So we get to use the properties of the expected value for random variables as you would, as you have been doing it before. So let's use them. And then what you have is expected value of a1, y1. Well, you get to factor out that constant, because we know that the matrix A is a matrix of constants, right? We have something similar here, and we know that the expected value of a constant is a constant. And we do the same here. Expected value of a sum of expected values, we have a constant here. Let's factor it out. Another constant here, let's factor it out by the linearity of expected values. And there, expected value of a constant, the constant itself. But now note that these expressions, you could rewrite those expressions as follows. The matrix A times a vector that contains as its first element the expected value of y1, and a second element the expected value of y2. So let me borrow this. And I think we also have, yeah, a vector with the expected values that we want. And let me borrow this guy here. Right? You guys agree that it's the same when you do the matrix multiplication between that matrix, that 2 by 2 matrix, times this vector, this 2 by 1 vector, plus this 2 by 1 vector, you end up with this, right? With that expression. But that is the same as that matrix A times the expected value of the vector y plus that vector c. Right? And that's exactly what the proposition is telling us. That the expected value of that matrix A times the random vector y plus c is the same as A times the expected value of y plus c. Okay? Now, think about our little example. Instead of 2 by 1, we could have an n by 1 vector, like we have here in the proposition. So instead of 2 rows, I would need n rows. This, we know, that's how expected values of random vectors work. So we would have also the expected value of y, the y1, the expected value of y2, up to the expected value of yn. This one, you know, you could change the dimensions of the matrix A, right, as long as it's conformable. So in this case, r rows, n columns. So we could have, instead of 2 rows, r rows, n columns, and then the multiplication A times y can be done, no problem. And then this guy, well, this guy needs to have the right dimensions, right? And those dimensions would be r by 1, because when you do that product, A times y, the product has that dimension, r by 1. Okay, so basically this would be, you could just rewrite what we did for this example but with matrix A with R rows and N columns, and then everything would be exactly the same. Okay, proof in the general case would be the same with more elements for the matrix A and more elements for the matrix for the vector C. Okay, anyway, so keep this one in mind because we're going to need it for what comes next. Okay, so what we said at the beginning of our video was that our main goal was going to be showing that beta hat is an unbiased estimator of beta. Okay, so before we do that, let me show you the model, the multiple regression model that we're going to be considering. We're going to be doing something similar to what we did with our proposition. I'm going to be writing down a particular case of a multiple linear regression model. I'm going to have only two predictors, like remember that example about a car plant? So something similar, right? Only two predictors, but then at the end we're going to see that our ideas can be easily extended to the case where we have k predictors. Okay, it's just that I don't want to write too much here. Okay, otherwise it's going to be kind of crowded. Okay, so that would be our first observation. We're just considering a classical linear regression model, right? We're not doing anything to the predictors, we are taking them as they are. So this is the first predictor, this is the second predictor, and that would be the model for the first observation. Let me borrow that, and now we have another observation, a second observation. Second individual, second error. Okay, let me do one more. We have a third individual with its particular values for predictors and the error, and then one more, the nth one, the last one. Okay, so we have an observed vector y with n rows. Okay, makes sense? Are we good? Okay, so as you can see, I'm using the second subscript to denote the predictor I am referring to. Okay, so in this case the second subscript is 1. In this case the second subscript is 2, and the first one lets you know which individual, which observation we are referring to. Okay, okay. Now, clearly, right, the expected value of y1 is just this, because let me remind you that our assumption is that the epsilons are normally distributed with mean 0, and variance sigma square. And we're assuming that the epsilon i's are independent. Okay. Now, so using those assumptions, it's clear that the expected value of the first observation is just going to be this, right? Because the expected value of a sum of expected values, these guys are constants, and this one, the expected value of epsilon 1 is 0. So we have something similar for the others. Let me copy these guys here. So expected value of y2, have this, expected value of y3, that, and expected value of yn, we have that, right? No problem. Now, as you recall, what we said is that the expected value of a vector is a vector that contains as its elements the expected value of its elements, right? So in this case, right, we know that that model here, you could rewrite that model like this: a y, a vector y, dimensions n by 1, x, a design matrix with a 1 and x11, x12 as the first row, 1, x21, x22 as the second row, and so on, right? So this one has, that design matrix has n rows and 3 columns, and we could have a beta, a vector beta, we could have a vector beta with elements beta 0, beta 1, and beta 2. Okay, so let me write that down here. That would be our vector 3 by 1, and vector of random fluctuations epsilon n by 1 as well. Okay, anyway, so the expected value of this guy, of the vector of the random vector y, would be a vector that contains these as its elements. You agree? So what we have here is that the expected value of y is just, guess what? What we have here is just x, the design matrix, times beta, where beta is a vector with elements beta 0, beta 1, beta 2. Okay, so that's what we have there. It's beta. There we are. Agreed? It is clear, right? That we're just rewriting this using matrix notation, and again, what we're going to be having here is an m by 1 vector, this guy here. Okay? Okay. Now, remember how we defined beta hat in the case of multiple linear regression? Remember the formula that gives you beta hat? What we said in another video is that that formula remains the same for simple linear regression or for multiple linear regression. So we know we know that beta hat, okay, let me find that beta. Now I need a hat. There we are. And in this case, let me be very specific about the dimension. It's a 3×1 vector, right? And the formula, right, is x transpose x inverse times x transpose y. Remember that? Okay, so x transpose, x transpose x inverse times x transpose y. Okay, which makes sense if you think about the dimensions. See that x has dimensions m/3, so x transpose is going to be 3/n, and then when you have that 3/n, let me talk about the dimensions here. So notice that x transpose x, so since x transpose is going to have dimensions 3/n and x has dimension n/3, right? The dimension of x transpose x is 3/3. So this is a 3/3 matrix. That's important. Now something else. X transpose y. X transpose y, right? X transpose is going to be 3/n, and this is going to be, well, this is m/1, so it's going to be just 3/1, right? X transpose y. And this guy is a matrix 3/1. And then it makes sense, right? Once you do the multiplication, 3/3, 3/1, you end up with a 3/1 beta hat, as you should, because we only have beta 0, beta 1, and beta 2. Okay? Okay. So it's important to keep those dimensions in mind, just to make sure that there's no mistakes here in the expressions that we have. Okay. Okay, it looks nicer. Well, so, but now, our main goal here is showing that this guy, this estimator beta hat, is unbiased. So, see that we have here x transpose x inverse x transpose times y. So, how about we think about this guy as a matrix A times y. And then what we want is we want to find the expected value of A times y, right? So by our proposition, we know that that is just going to be a times y, right? So using our proposition, expected value of a matrix A fixed, right? It's just constants, times y is just going to be A times expected value of y, okay? But the expected value of y is x beta, right? So in our case, A times x beta. But now we plug in what A really is, okay? So this is what A represents, times x beta. And then we realize x transpose x times x transpose inverse, that's the same as the identity times beta. But the identity matrix times beta is just beta. And we are done. We have shown that the expected value of beta hat, our estimator, right, is the parameter of interest. So beta hat is an unbiased estimator. Okay? And note that in this case we didn't have to do the proof separately for the elements. We didn't have to do this 3 times, for instance, because we have beta 0, beta 1, and beta 2, right? We didn't have to find the expected value of beta hat 0, the expected value of beta hat 1, the expected value of beta hat 2, right? No, just like that, okay? Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.